somewhat a more complex example where the data is a little bit more complex and see how we can do principal component analysis and how can we do PCA on that, right? So let's use the PCA and SVD on a slightly complex data set. So what we are doing is we are essentially importing the NumPy and matplotlib libraries here, and first thing that we are doing is we are randomly generating some isotropic data, and so using this random number generator you can see that we have generated this data set, right, which has number of points, and if you can see the plot, right, the data has two features or two variables, x and y. X ranges between a value of -4 to 4, y goes between a value of -10 to 10, okay, and it has a significant spread across both the x and y. Okay, and as usual, x is the one unit vector which is 1 0, and y correspond to 0 1 direction vector, and essentially we have 100 data points in this overall data sets, right? So first thing that we will do before we carry out any analysis is we will do normalization, and this is something that we have discussed in the in the previous lecture, that given a data, it is always a good idea that you normalize that data. So this code block essentially implements the normalization step, right? And what we are doing is we are normalizing this overall data that we generated, and if you normalize that overall data that we have, obviously for both the axes, because of the normalization, right, it will go between a value of -1 to 1 both for x and y, okay. But still you can see even after normalization of the data that we have implemented, there is still spread in both the axes that we have. Okay. So with that, let's move on and let's see how much variance is captured by each of the features x and y. So the x and y, how much of the feature and variance is captured. So we have done this variance computation in this code block that is out here, and we output the result of this variance computation. So the variance of x is 0.034 and the variance of y is 0.035. So essentially if you convert that into percentages, you will see that the 48.93 variance is captured by x and 51.07% variance is captured by the y variable that is there. So in this case, right, for the plot that we have, it turns out both the features are nearly equally important and they're capturing important aspects. So dimensionality reduction might be a little bit tougher in this case, right? So discarding any of them, we will lose significant information. Okay. So what we are going to do is, if we take a close look at this data, we will see that data is most spread out in about an axis which is approximately 45 degrees to the x-axis. So if you look into this data set, you will see that approximately at 45-degree angle, the spread is the most, right? So let's visualize this spread direction, and so I have this code block which essentially gives these two directions which are created by this solid red line and the dotted green line that you have, right? And what are these lines? We can see that the data is most spread about the axis which is spanned or which is depicted in this diagram by the red solid line that we have, right? And the data is least spread about an axis that is essentially normal to the solid red line, and it is represented by the green dashed line that you can see on the screen that you have. Okay. So what we are going to do is we are going to be using PCA, and the PCA is essentially going to identify these two directions, the red line direction and the green line direction for us, and that's the main function of the PCA. It will essentially find out those two axes along which the variance is going to be the highest. Okay. So again, when we are using PCA techniques and identifying this direction, what we are getting, the eigenvector corresponds to the direction. So when we get the eigenvector, we will get the direction of this red solid line, and also we will get the direction of this orthogonal dashed green line. Okay, so that is what is going to happen, and the eigenvalue corresponds to the spread or the variance. So the eigenvalue tells us how much variance is occurring along those two solid red and the dashed green lines that we going to be there. And it turns out there will be more spread along one dimension than what can be possible in the other dimension that is out there. Okay, so let's do the computations that we have here. What we are doing here, we are first computing the covariance matrix X which is essentially x times multiplied x transpose times x, okay, and then we are taking the eigenvalue of the covariance matrix X, okay, and then we are printing the eigenvalue in the ascending order and the corresponding eigenvectors. So what we are doing is like we are taking the ascending orders and we are picking the important ones, and then we are finding the corresponding eigenvectors, and then we are finding out the percentage variance captured by the each of these eigenvectors. So some of the results that you are getting is the eigenvalue in the ascending order for the data set that we have shown you previously is 0.0652 and 6.9257, and corresponding eigenvectors are given here, okay, and the percent of variance captured by the eigenvectors in the ascending order is 0.93 and 99.067, okay. So if you want to interpret this result, right, the direction that captures the maximum variance or spread is given by this vector 0.694 and 0.7148, and it essentially captures 99.06% of the variance. And the direction corresponding to the other eigenvector is given by this vector, which is minus 0.7148 and 0.6994, and it captures the remaining variance, which is equivalent to 0.933% of the total variance. So what has happened, the original variances, which was in the x direction 48.93 and in the y direction 51.07, got aggregated and transformed, and in the new red and the green directions, those variances are captured by and the magnitude of 99.067% and 0.933% and so on, okay. So this is the way to interpret what is happening, and then from the the eigenvectors that we have found output, we can essentially create a matrix of eigenvectors, and this matrix essentially acts as a rotation matrix, and when we multiply this rotation matrix with the original data matrix X, it essentially projects that into a PCA space, right. So that is what we are going to be doing. So in order to determine the value of X in the PCA space or the transform space, we will basically use this vector matrix V, which is the matrix of eigenvectors, and we will multiply that with the original matrix X. So X times V will essentially give me the projection in the transformed space that is out there, okay. So again, let's do that. So what we are doing here is we have computed the principal component, and then what we are going to be doing is we are going to be plotting the transformed vectors in the transform space that is out there. So this code box essentially does that. So when we do the transform space, you can see the figure that is on the top, in the right hand side is essentially the principal component data set when the axes have been rotated, okay. So we can see that we can capture almost all the variance in the data only using one axis, right, and this corresponds to the primary principal axis. And in the original coordinate, the dominant eigenvector is essentially the 1 1 direction, which is basically the 45-degree angle that we have, and essentially it captures the 99.06% of the variance that is out there, okay. Now what we can also do is we can do reconstruction. So we have this XPCA, which is X times V, and from that we can get the X reconstructed. And what is X reconstructed? It is essentially equivalent to XPCA times V inverse. So if you take the inverse of the V matrix, which is basically the inverse of the eigenvector matrix that is there, and multiply that by the XPCA, we can reconstruct the X and see whether that X is equivalent to the original that is there. So if we really have that, then we can do also the reconstruction using the the steps that has been shown here. So let's continue the same example and see how we can do the SVD, principal component analysis, using a SVD based approach, okay. So for this example, the X is a complex data set, and we are reusing the same X that we have used for the previous example, right. And what we are going to do is we are first taking this X, we will normalize this X, and this is something that we have performed previously, which is the normalized X data. And then what we are going to do is we are going to take an SVD, or we will do the SVD decomposition on the normalized matrix X, and that is what you see on the screen here, which is dot SVD, and then in round parentheses you have X underscore norm, which is essentially telling you that we are doing a SVD of the X norm matrix, okay. And that has been stored in those three matrices U, S and V. Okay, again, dot SVD returns the eigenvectors in the descending order. Okay, whereas the EIGH method, which we have used previously, it returns the eigenvector in the ascending orders. Okay, so if you want to compare, the performance and how the eigenvalues of SVD compares with the PCA approach, this is the code block that does. Right, so you can see that SVD is representing the eigenvalues in the descending orders. Okay, and the eigenvalues obtained from the SVD essentially matches exactly with the eigenvalue that we found using the PCA based approach. Okay, so we can print and we can verify that. And again, you can look into the eigenvectors that you get out of SVD and also the eigenvectors that you get out of the PCA based approach. Those eigenvectors are also exactly the same. So the eigenvectors have obtained from SVD matches those with the eigenvectors that is obtained from the PCA based approach that is out there. So again, you can use either a SVD based approach or a PCA or covariance based approach to do the principal component analysis for any given data.